Hello, this is our first entry in the series of computer architecture, and in this first session, we'll be taking a look at what's inside the CPU, how it works, starting off with a very simple basic example, and then slowly throughout the lecture, working our way up to a more up-to-date and complex example. A couple of disclaimers. Obviously, we will not be discussing what's inside a modern CPU. We'll be leaving that out for future sessions. Nevertheless, we will be exploring a couple of the basic building blocks as well as understanding how these building blocks came to be and interact with one another. All the small code snippets that we will be exploring in this session will be C code. And a last disclaimer, for those that are most familiar with the subject, this is a watered down version in order for it to keep within the time frame of this talk and allow it to be as accessible to most people as possible. Without further ado, let's get right into it. So today's agenda, we'll start out with a very quick overview of what a CPU does, and in order to build the small fundamentals for this talk. Then we'll be looking at the concept of pipelining, its use cases, and the challenges associated with it. And then later on, we'll be building upon this concept of pipelining and expanding it to superscalars and introducing with that the concept of outer order execution um, with the concept of schedulers and reordering. Let's get into it. So, a quick overview. What does a CPU do? Well, a CPU is something that executes code in a very high level abstract fashion. So let's say I'm writing my code. So I would write my human readable code in C, for example, and I would make it go through a compile chain. So I would first take my code and put it to a compiler. Then at some point I would obtain assembly code, and then I would feed in this assembly code through my assembler in order to obtain binary. So here you can see that I've made the transition from something that is human readable code, for my C code, into something that is called machine readable code, which are my binary instructions. And these are the ones that are actually going to be executed by my CPU. So abstractly, what happens? So I've got my CPU and I'm going to feed it my instructions, so my binary instructions, which is going to tell it what to do. Instructions, you can think of it as my instruct my CPU what to do. And I'm not going to do things without a concrete base. So I'm also going to feed it data on which my CPU is going to do stuff. And this process of giving it data is going to generate new data. And so I can group these three aspects, my instructions, my data, and my generated new data as, well, their memory. And another way of seeing it is that my CPU manipulates memory. It's as simple as that. But what do I actually mean by manipulate memory? Well, I'm going to break this down into a couple of points. First, in order to manipulate my memory, I need to get my memory, so getting my data on which to do my manipulations. Once I've got it, I want to do my modifications on this memory. Afterwards, I want to be able to store my data back into my main memory. So I've brought in this data, I've done my stuff on it, and then I want to push it back to my main memory for the modifications to take place. Because if the modifications of my data are isolated in my CPU, well, that doesn't really help me much. And what do I actually mean by data when I say get data and write back data? Well, in this case, when I say get data, I'm talking about my instructions in my data memory. So by data memory, I actually mean my program variables that I can manipulate. So let's say I'm writing my C code. These would generate my instructions, and then my variables would be this data memory that will be manipulating. So let's break this down into steps. This idea I'm going to convey with these five stages that my CPU is going to have are actually from a CPU model quite common in academia called the MIPS. And the MIPS has 5 stages, the first stage of which is fetch. So fetch is where I'm going to go and get my instructions. So I'm going to have a program counter, which is going to follow at which instruction I am. And based on the value of that program counter, I'm going to put in an instruction. This is going to be the fetch. So I've pulled in my instruction. What goes afterwards is decode. So I'm going to take my instruction that I've pulled in and then pass it to decode. So decode, as the name suggests, is going to decode this binary instruction into the signals that I'm going to use to tell my CPU what this instruction actually means and what I need to do with it. Then I'm going to have the execution block, on which I'm going to do the stuff specified by my instruction, depending on the instruction. Then I'm going to have a memory block. So this is where I'm going to be able to have my interactions with my external memory. So my loads and stores from external memory, that is not my CPU memory. And then I'm going to have the write back, where I'm going to write back the data that I've modified into my internal registers. So I've got my external memory, which is outside of the scope of my CPU, and then I'm going to have my local registers that I'm just going to refer to as registers. So let's get a more concrete example. So I'm going to fetch an instruction in my first stage, and then I'm going to decode it. And during this decode stage, well, I've just realized that the instruction I'm processing here is an add instruction, in which I am going to add to my value A, which I am assuming is already in my CPU's local registers, 1. So what I'm going to do is actually simply A equals A plus 1. So now that I've decoded this, I'm actually going to execute this in my execution stage. So this could probably be done by an ALU, an arithmetic logical unit, which does interior calculations. Afterwards, from my memory stage, well, I'm not going to do anything. And then, so this is going to be a wasted stage in a way. And then, write back, I'm going to write back the results of my new value of A into my local registers. Now, let's look at another instruction. So, fetch as usual, I'm going to get my new instruction, and I'm going to decode it. And here, I'm actually going to have a store. So, my instruction store A address is going to store my value of A to some virtual address specified by A address. I'm here again working on the assumptions that both of these values are available to me. So during my execution stage, I'm actually not going to do anything. And then I'm actually going to do the store operation in my memory stage. So I'm going to send out my data to my external memory to be written at virtual address A. And then during write back, I'm also going to not do anything. Okay, now our last example. Fetch stage, I think you guys get the point at the here. Gonna fetch some new binary instruction. Decode, oh, I've got to load B to some virtual address B address. So here again, execute is going to sit idle. And then I'm going to do the load instructions. So I'm going to get data from memory. So here I'm going to get from the virtual address B address some data that I'm going to store into my local registers at what I'm going to refer to as B. And so I'm going to write this back, write the data I've gotten back to B during my write back stage. And so I think you're starting to notice a couple of problems of underutilizations of these pipes. Just keep this idea in mind for later on. Now, I've got my 5 stages, and I see that my 5 stages here. Let's suppose that going through this 5 stage takes an entire second. How could I actually help bring that frequency up? And so my CPU is running at 1 Hertz. So I'm doing 1 instruction per second. Now, the concept of pipelining is actually going to help us boost a little bit this frequency. How does it work? Well, if my entire 5 stages take 1 second, I'm going to suppose as a hypothesis that all of these are perfectly balanced, and so all of them take 0.2 seconds. So the idea is I'm actually going to segment these and make them isolated from one another. I'm going to put flip-flops in order to store the data between each of those stages. And the basic idea is that my data actually is at one point only in one of these stages, while the other 4 are sitting idly. So I'm going to use this in order to speed up my execution. So here I've got my 6 example. Currently, I am not pipeline. So going through all of my stages, so here I've got a model with 4 stages, but you can extend it to 5 stages, is actually going to be sequential to my next instruction. So I have to wait for my data to go through all of my stages before I can actually get another instruction and do the same thing on another instruction. Now, what if I could better utilize this by pipelining them? So in order, the idea here is that immediately after I've finished my fetch stage, I'm not going to sit idly waiting for my instructions to go through all my stages here. I'm going to bring in another instruction and then stack it right behind it. And the same goes for my 3rd, my 4th, my 5th instruction. And you can see how I can pack this way more fuller and better utilize my resources. This is the concept of pipelining. And so now that I've segmented this, each of them still takes 0.2 seconds, but since I can once I've gotten one instruction through the fetch, get another one through the fetch, this means that when I get a lot of instructions going, each instruction actually only takes 0.2 seconds to execute, because every 0.2 seconds a new instruction has finished executing. So I can see this as my core going at 5 Hertz, because I'm doing 5 instructions per second. Now there are a couple of problems with this idea of pipelining, and one of them comes with branches. So I've got this very simple code right here. I've got 2 variables, A and B. A has a value of 10 and B has a value of 4 initially. And I've got this branch condition where I'm evaluating the value of A and saying, okay, if A is greater than 10, then do A equals A minus 1. And if it's not, well, just don't enter that branch. And so I've got a condition where my branch is taken, so I'm supposed to do this instruction next, A equals A minus 1. And if it's not taken, well, I will just get the next instruction after the brackets, which would be working on B. And the problem is that the evaluation of this branch condition, A greater than 10, is actually done in the execute stage. But as I am pipelined, I have to decide once my instruction is actually going to be in the decode stage, if I'm actually going to bring in the instruction for branch taken or the instruction for branch not taken. And let's say that, and I'm going to, at one point, I'm actually going to have to guess and speculate. What am I going to put inside of fetch and then also decode between the moment I've gotten my conditions and the moment it's actually resolved? And if I guess correctly, then these two time slots are going to be well occupied. And if I don't guess well, then I'm going to have wasted a certain amount of instructions. So let's say that I'm going to suppose that my branch was taken. So I brought this instruction in for my branch condition, and then when this one went to decode, I fetched this instruction. If everything goes well, no problem. But if I mispredicted, and this one was actually a wrong prediction and turned out to be false, like is the case here, then I've wasted a certain amount of time slots, and I need to purge, in a way, this instruction from my pipeline and make sure it was never executed, because it should have never been executed in the first place if we had followed the correct program flow. And so in order to help with these branch resolutions, I'm going to speculate using something called branch prediction. And branch prediction is simply to speculate on the outcome of a branch based on information extracted from the branch historic outcomes and other sources of information that we will not be exploring too much in detail today. So let me give you a very simple example. Here I've got a 1-bit saturating counter for my branch predictor. Very, very simple branch predictor that works by looking at what was the previous outcome of a branch. So here I've got this very, very simple while loop, while through a equals a plus 1, and I'm simply going to loop through that. And how will this work? Well, let's say that in this first condition here, I predicted not taken. So when this got to execute and I saw that it was actually supposed to be resolved at taken, I'm going to change my prediction to taken. And then as long as I keep predicting correctly taken, I'm going to stay in this state. And so here, even if let's say I mispredicted the first time around, then I would still keep predicting taken and will stay in this state and predict correctly forever. This is an example of the graph of how this works between all the states. So as long as I predict taken and it's taken, then I'm going to stay in my state. And if I mispredict and it was actually supposed to be not taken, then I'll change states. And if it's not taken, yeah, I'll keep in that state and just stay there. And obviously, this has a couple of drawbacks. This is a very simple code just to show that, well, it isn't always the case. Here I have two loops where here I'm supposing that I only have one branch, but here I have two branches, and so the fact of having a couple of different branches means that I'm actually not going to track the correct branch, and so sometimes this time one time on two it's going to be taken, and the other time it's going to be not taken, and here it's always going to be taken. My branch predictor is simply going to screw up. And so in order to overcome this, we're actually going to have to introduce more and more complex branch predictors that we will not be exploring today. But just to tell you, this is a very, very rich field, and I think you can understand why it is, seeing that we're going to have to scrap a lot of our CPU's work if we mispredict. Here's an image of a cat, just to keep you with me, because branch predictors are a little bit complex. And let's get right into this back. Okay, so you remembered how I told you earlier on that not all instructions are utilizing our pipeline really efficiently. Some of them are not using the execute, some of them are not using the memory, some of them are not using the write back. Wasted. And so the idea of superscalars is to separate my pipeline into specialized pipes, where the instructions are actually going to go through these specialized pipes. And so I'm going to reduce the number of cycles that I have to do for each instruction, or make them longer based on what my instruction actually needs to do. This is obviously going to help us with frequency, it's going to help us with power, and it's going to help us just get something more efficient overall. So here I've introduced 3 different pipes. The first one is for ALU, so this is going to be for a integral calculation, so my arithmetic logic unit. And if I have an ALU instruction, here I can see that I'm going to have to fetch, decode, ALU, and write back. So a 4-cycle execution for my instruction. Then I've introduced memory, so these are for our loads and stores. Here now, if I have a memory instruction, then it's going to take only 5 cycles. And if I have, I've introduced also FPU, so this is for my floating point arithmetics. And in this case, more complex, it's going to take 6 cycles. So let's see how this would work. So everything here seems nice, okay, but obviously it isn't. It's more complex than that. So here's an example of a simple code. I've got first line and second line, a couple of arithmetic ALU math. Then third line, I've got a multiplication on floating point variables. So I'm going to convert A and B to floating point variables and then store that in C. And then I'm going to have in the fourth line a store operation on this variable that I just calculated in my third line. So this is what we could expect in the perfect world to happen. I would have my ALU and ALU, line 1 and 2 being executed here. And I have something which is called forwarding that is going to happen, where if I have a variable here being A that I'm currently writing back to memory, but I see that I need it just in the next instruction, then I actually have the ability to not only write it back but also forward it to the execution stage of the following instruction, because well, it's already been calculated. All I need to multiplex it so that it can also be directly reused by the next instruction, still pretty close to me in my pipeline. We will suppose that this ability to forward data extends for all of our following graphs. Now, so I've got my 2 ALUs, and then I'm going to also forward my new value of B through my FPU. Now I'm actually going to have a problem in my 4th instruction here, because as you can see, I want to store the value of C, but when I'm actually going to start my operation on my memory, the value of C still hasn't finished being calculated. So the value of C if I was to execute this now, the value of C would be wrong. So I'm going to have to introduce a couple of stalls where I'm actually going to say, okay, I'm waiting for this calculation to be finished, and once this calculation is finished, then I can forward it and to my memory. So I've got to introduce at minimum 2 cycles of stores that are going to propagate through my pipeline. Obviously, this isn't very efficient, so could we possibly better utilize this? Could we do something else while waiting for our data? And this is where I'm going to introduce the idea of the scheduler. So the scheduler is going to be put in front of my different pipes, and its role is going to be, when I've got these kind of conflicts, this inability that would result in potential stalls, to plug in the holes with the other instructions. So these other instructions could come from future instructions or past instructions. The idea is that I'm going to reorder my code in order to better utilize my internal hardware resources. The problem is that by reordering my code, I'm going to modify the order in which my code is going to be executed. And that is at risk of breaking one of the fundamental contracts between my CPU and my programmer. Is that my programmer expects to write sequential code and expects the illusion that his sequential code is actually executed sequentially on the CPU. Imagine doing a plus 1 and then c equals a plus 2 and having different values of a. That would just break everybody's code. So I'm going to have to build the illusion that my code is being executed in order. And I'm going to build this illusion by introducing something called a reorder buffer. So this reorder buffer is actually going to store my finished variables until the moment where all the previous instructions have been executed, and only when that happens is it allowed to write back to memory. And this process of writing back is actually called committing. So when all the instruction that came before this was expected to be written back have been committed, then only can my next instructions be committed. This helps us maintain this illusion that is so important to us. Now, obviously, in my previous example, I only had one fetch and one decode unit. But now with my numerous pipes and my ability to move around instructions, I can really push more efficiency out of this and use a scheduler to make sure that all of these are fed to a maximum and none of them are starving, meaning none of them are just sitting idly by. And so I'm going to increase the number of instructions I can fetch per cycle by giving me more fetch and more decodes. And all of this is going to be rescheduled within my scheduler according to the size of my schedule, something called schedule window. Obviously, the problem is that when we get more instructions coming in, we also have to increase the number of instructions being able to be written back at every cycle. So we're going to widen this on both sides. Okay, I hope you guys had a great time. This was a very simple overview of how the CPU core works internally. So, quick reminder, we started from a very basic overview of what was a CPU. Then we introduced the concept of pipelining. We glossed over a little bit why we want to bring in branch prediction into that. Afterwards, we looked at how a simple pipeline predictor with linear stages led to less than ideal utilization of my resources, and so we broke that out into different specialized pipes with the superscalar approach. And then we showed how superscalar, with the difference in number of execution cycles of my different pipes, introduced the potential stalls, and we could mitigate that by introducing the idea of out of order execution with the scheduler. And in order not to break any of the programmer's assumption, introduce the reorder buffer. And then we took this idea and widened the number of instructions we could fetch and decode each cycle, while as on the write back side, in order to really help us push every single bit of additional computation power out of our CPU. I hope you guys had a good time and hope to see you next time on Computer Architecture number 2.